QM, everybody. So, welcome back. Quick disclaimer as always, the discussions today are not a solicitation for investment and is not financial advice. The Quill and Wrapped Quill tokens corresponding to the network are utility tokens, and we do not condone or encourage speculation on the utility token of the network, or any other tokens that may come up in this broadcast. So, with that, let's go ahead and get started. First, we'll talk about the basic news that's happened. I think a lot of you already know what it is, but we'll talk about it anyway. And then we'll go ahead and move into a few different topics for today. This is a combined dev stream. Normally these are on the weekend, but obviously there's some stuff that's happened and we're going to talk about that. But this is going to be a combined dev stream plus, talk about Q21 updates, the journey that got us there, and a few other tidbits, plus a little preview of some other stuff coming to Quorum Mobile in this week's beta release. So, to go ahead and get started, obviously, news, if you aren't actually running a node and aren't following on the socials or anything, 2105 finally released, which unlocked our enrollment process. Things are moving and grooving, and we are steadily chugging along through this enrollment series of steps. There are a few things that some people have noticed by operating their nodes. A few small bugs, like restarting the node after having launched once causes a weird issue that will basically require some storage maintenance before you can actually get it to restart. We're going to fix that, and it'll be rolled out in a 2106 release sometime between this evening to tomorrow morning my time, or this morning your time if you're in Europe, to later afternoon. Needless to say, enrollment has been going along. It's been working at a relatively steady pace. There's been a few fun stumbles, but it's actually ultimately a reflection of what is good about 2.1 and some of the broader objectives we've been trying to fulfill. So to start things off, we were able to get the enrollment to kick off around, doing some quick mental math here, around 10 p.m. or 11 p.m.-ish yesterday UTC. That's great. Was a little bit of a rough awakening for me. As it turns out, I tried to sleep and set alarms for when signing was done, and I made the tragic mistake of not checking my phone. My phone died, and so I woke up late to a, unfortunately, late notice of the signing being done. So we kicked off enrollment a little late, but we are moving and grooving, so that's great. Looks like, oh god, I hate this spam crap. Anyway, thank you, AutoMod feature of Twitch. So, things are going. That's great. We're going to be, obviously, as I said, we're going to be making the 2106 update to resolve some of the minor issues people have reported. There's also been a few reports around the master proxy behavior. I talked about it in a previous stream. I'm investigating that, and that'll also get rolled into the 2106 release. Just so you know, there's still plenty of time. This enrollment, like I said, there's been one of our archive nodes isn't running yet, and so by consequence, it's caused the overall consensus to basically skip them every time their round comes up, and so by consequence, we're not at perfectly 10 frames a second. It's kind of closer, anywhere between roughly 12 to 15 seconds per frame, which means that we're looking at a time of roughly, I would ballpark it to like about 24 hours from now for enrollment to be fully concluded. So still plenty of time. If you haven't started your node, you got time. If you're worried about not making initial enrollment, you're going to be fine. So all that out of the way, obviously super excited because God, this has been one hell of a ride to get here. So let's talk about that. Let's talk about the journey that led to 2.1 in the first place. So about, God, at this point, over 8 years ago, I had originally started this project. At the time, it was called Howler. And some of you already know this history, so it's going to be a bit of a repeat, but it's worth saying. I started this project called Howler, and the purpose of it was to build an alternative to Discord, mostly for the purpose of teaching others how to build applications at world scale. You know, the kind of scale that you'd be doing as a senior or staff engineer at a large company. And through that process, I was basically building out what I thought was a cooler Discord. And so by consequence, I was like, hey, I want to launch this. But there were some things that, got in the way of that. At the time, there was a lot of censorship going on Discord. There was this whole issue with Wall Street bets and their particular community having a certain word to refer to one another. Unfortunately, the same word I can't even say on Twitch. So, it's just there's certain in-group behaviors that are culturally acceptable within the group that Discord didn't find acceptable, and by consequence, that group got banned, and that was a pretty big deal at the time. And so it reflected something important to me. One, arbiters of control of content is not an acceptable solution when you're operating at world scale. And there's been no company that successfully, operated in the context of truly preserving free speech, especially at that time, at global scale. And the reason ultimately comes down to a couple of different factors. One, there's governmental pressure, as we saw during COVID with the things that Elon exposed after he bought Twitter. There's been this phenomenon of governmental pressure to try to push party lines, which in that case was regarding COVID mandates and any sort of potential criticism being swept under the rug. And it's great that, it happened that information was revealed, but there's plenty of cases where this information isn't always revealed. So you have cases of different governments pushing these social media providers to suppress content in their country, to try to monitor and scrutinize people within their country. And it's just an unacceptable situation. And that comes from, ultimately, being a centralized service. And so that brought me back around full circle to revisiting how I was building this Discord alternative. And so by consequence, I started thinking, how do I decentralize this? Because if you look at crypto, you look at at the time we were dealing with basically Bitcoin, Ethereum, Solana, those were the big three. And none of these, even Solana being known as the faster one, was capable of operating at a scale of processing transactions at a rate even comparable to a reasonable messaging service. And you've seen dozens of different projects come out that were trying to do messaging services, and in a decentralized way. And always it converged back into, one, let's put it on a blockchain, and two, let's charge fees for every message. That'll solve the spam problem. Well, unfortunately, it's something that we actually learned well before Bitcoin even existed. It was back in the days of trying to solve the spam problem with email before, Bayesian filters and all the kinds of deep, scoring systems for different email servers came into play, and then we, ended up in this kind of centralized set of monoliths of Microsoft, Google, and Amazon now for email services. There was this idea that circulated in the cypherpunk forums talking about an idea of basically putting a digital postage stamp on an email. But obviously people aren't going to pay money to send an email. They're already paying money for their mail server. That's stupid. So there was this idea called hashcash. And hashcash was this concept where you would basically iterate through a hash function, like in the case of Bitcoin, using SHA-256, for the purpose of reaching a random number that had enough zeros at the beginning of it, because it was a 256-bit number, such that it was sufficiently, it took sufficient amount of computation in order to generate that hash and thus produce a winning number that constituted proof of work. And that's ultimately the inciting incident that led to the entire foundation of what ultimately got used in blockchains. And so this idea was useful for trying to solve the spam problem because it wasn't financial, and instead was something that anybody who was reasonable, that was just trying to send an email at a regular rate, could reasonably produce. But for spammers, it was too complex to do. And so thinking things from, the very brass tacks, how can we go full cloth from all the crypto tech that had existed at the time and revisit the problem at its core? How do we solve decentralized distributed messaging? That's what I was after. And what I came down to, that's funny. First off, that's a ridiculous username. But second, no, it doesn't only exist on Ethereum. The network is live, buddy. So anyway, what I was trying to get at was how do I solve this problem from a decentralized point of view? And so from the decentralized point of view, we need something that's capable of actually performing, at that kind of scale that we need. And you can't solve it with a blockchain. A blockchain essentially has a bandwidth constraint that's too limited to have sufficient throughput. And so I started piecing together some of the other inventions that were coming out of the crypto scene, because it enabled trustless compute at a scale that was perfectly reasonable, but without having to run into some of the issues that you get when you're trying to coordinate global consensus of state around all state all at once. That's how you end up with the scaling limitations. And so by consequence, I ended up started building out all the underpinnings of what it would require to build this decentralized Discord clone. And ultimately, as I was building this out, I realized I'm building out basically a decentralized AWS. So around 2019, I decided to rename the project, and I just thinking because it's not just a Discord clone, it's actually really a decentralized AWS, so I should just like rename the project and focus on the raw part of the project, what it's actually trying to achieve. And that's how Quilibrium came to be. And so here we are today, and that's incredibly awesome that, after all this time, we finally have things working, enrollment is processing, and things are going great. But at the same time, now we're at this point where we had way too many nodes on the network. We were woefully underprepared for handling the kind of scale that people were going to throw at it for the purpose of mining. And by consequence, we actually ended up being one of the largest clusters of compute that was just out there for the sake of, at the time, was just purely mining a coin before we were even ready to roll out all the feature upgrades. However, that ended up actually being a tangible benefit for us because it ultimately resulted in us having to solve problems before they struck us at the point where we've had all the different functionalities we wanted to have on the network. So over time, we overcame those problems, we solved them, new problems came up, as happens through the progress of the idea maze, and ultimately now, today, we are finally at 2.1. So from that, I'm very excited. Like it's a very cathartic moment. It's been a long time to get here. So let's go ahead and talk about what we've learned from this launch, what we need to do next, what people can expect to happen next, how to diagnose your node, like how when you run one, what you can expect to have happen, how you can basically determine whether things are happening at a healthy state, and so on. So I'm going to pop over to VS Code. Just bear with me one sec because I've got a single screen set up for this and it kind of sucks. All right, cool. So let me check this real quick. I don't know why I'm having issues. There we go. Okay, great. So, all right, I have 6 terminal windows pulled up. And the reason I have this pulled up is because I want to demonstrate what a fresh network looks like. And so you can see all the different operations that are happening. And I'm going to run some in debug mode. I'm going to run some not in debug mode. So this will give you kind of an idea of where, when you're running a node, where things will be at and what you can expect to see. So presently in the node folder, I'll just go ahead and build again just in case, because it's been a bit. Great. And then I'm going to go ahead and remove all of the config store folders and start fresh, because I don't remember if I did that before I started this. It's been a lot of pandemonium trying to get to this. All right, so let's go ahead and hop into one of the config folders real quick. When you start a node, and the way that we've been starting nodes is through the node application. There's a couple of different feature flags that exist, and it'll be along the lines of debug to turn on the debug mode. You'll have config to specify a specific config folder. And then also, if you're doing a lot of testing, like you built it locally, you'll also have signature check equals false. And that'll skip the signature check that happens in our production builds. All right, so looking at the config folder real quick, when you start a node for the first time, it'll generate the config folder for you if you don't already have it. And in that folder, you'll have a couple of different files. In this case, we have a config.yaml, keys.yaml, and presently a worker store because I didn't delete it because it doesn't matter at the moment. And I'm going to pop into this config YAML folder. You're going to see some private keys. They're useless. And so I already have it set up where I have 6 nodes. They are all bootstrap peers, and they have, obviously it has a pure private key. And one of the things that you'll do is you'll generate another file, which is the keys.yaml, and that contains the prover key. And what you'll want to do if you're making a local cluster in testnet mode is you'll want to grab the public key of each of these. So I have config or .config, .config 1, 2, 3, 4, 5, so 6 config folders. And I've pulled out all the keys and then brought them into, whoa, there we go, into this Genesis seed. So it's just the concatenation of all of those public keys. And that's how you set up your initial Genesis for testnet mode. And so what I'm going to do is I'm going to go ahead and pop down into another folder, and we're going to run node config is config. And actually I'm going to put this command first, debug, and of course signature check false so that we don't have to deal with that. And I'm going to copy this over into here. Oh, I did not increase the size of all these. Shoot, should have done that ahead of time. That's what I get for doing too much too quickly. All right, and then we will okay, so now we have our config folders set up. By the way, this stream is recorded. You will be able to watch it again. We've got a lot to cover and roughly 2 hours of time to cover it in, so I'm gonna be talking a little fast. So don't worry, you'll be able to rewatch it and see things through. So anyway, I have the node command set up. Gonna go ahead and run it, run it, run it, run it, run it, run it. And okay, now we have all 5 or all 6 running, and they are going to do their initial Genesis process. When you run in debug mode, you're going to have like warnings with stack traces. On production mode, warnings don't include the stack traces, but errors do. Just something to be aware of. Once it goes through this initial setup process, then we'll be able to... there we go. Okay, so now it did its Genesis, and it's going to be sending timestamps, and the timing of things is a little bit slow, so just give it a second, and it will be able to sort stuff out. Well, that's fun. Why am I seeing a... Oh, shoot. I know what I did. Okay, so that's on me. All right, I'm going to clear that out and restart. So what I'm going to do is I'm going to clear out the config store folders. And I'm going to just make this all a one-shot command so I can run this again if I need to. But the problem there that I forgot to mention, and I forgot to mention because I didn't do it, is I just ran that and ran those 6 nodes on mainnet. So let me fix that. All right, config 5 store, and we're good. All right, so let's try that again. And this time, network 1, so that we're actually using our own internal Genesis. That's on me. And I'll also go ahead and remove the debug from a few of them because, like I said, we want to demonstrate both scenarios. Oh, there we go. All right. Cool. And you can see what I mean right here. So the warning messages are now, without the stack traces. You only see warning messages when there's errors. So, okay, it immediately set up the Genesis. It's already entering the first rank. So a rank in this consensus algorithm that we switched to is essentially a separate concept from the frame number. Like frames will progress monotonically incrementing, so too will ranks, but ranks can be a success, like the frame has been accepted, or it can be a timeout because either the peer wasn't there or they suggested a frame that was invalid. Doesn't really matter. And so what you're seeing right here, because these are all participating as archive nodes, is you'll see them all engaging in consensus itself. And so that'll take a few. And so now we're into rank 5, and you can see that it's been capturing votes and it logs all that. I'm going to go ahead and stop one now. We'll still keep consensus going because we have sufficient coverage. And then I'm going to go ahead and edit config 5. And we're going to go and drill into the archive archive mode, and I'm going to set it to false. That is the default setting. I forgot to mention that I already had that set as well. And now we're going to go ahead and run it as a non-archive node. And so you can see that it starts all the workers now, because when you're in archive mode, the only worker is the primary node managing global state. And for a regular node, you'll see more than that. So we'll go ahead and let it sit. It'll get frames sent to it as the part of consensus continues. And so the first thing you'll notice is obviously not a whole lot. You're not seeing a whole lot. And the reason you're not seeing a whole lot is because the like frame processing that happens, I mistakenly put into debug logs. So running with debug, and so obviously it's a lot noisier of logs, but you'll see it start to spawn the workers. It does a certificate check that authenticates the connection between the workers and the master process. The reason we're doing that is because if you followed our upgrade guide, you'd know that these ports need to be open and accessible for others to connect to it. Otherwise, it can't be a very good worker. Otherwise, it wouldn't serve any requests. So going to go ahead and wait a few. You can see that frame 11 already arrived. And because we restarted these nodes pretty quickly, I think it might actually just go ahead and re-snap to the latest frame. And if not, it'll take a few, and I'll explain what's happening when it does that. Okay, so you can see one thing that's happened here is that there was a timeout, and the reason there was a timeout, you'll notice in the consensus logs, which, by the way, these consensus logs will appear for your workers as well. Where are we? Okay, so we generated a proposal as a leader because we were the leader for rank 14, and so we generated the proposal, sent it out, and then once it was processed, we moved to the next state, and from there, now we got the votes. Then we proceed to the next state. And when we were there, the next prover was actually going to be prover number 6. And prover number 6 isn't running as an archive node now. And so by consequence, it's not participating in global consensus. And so that basically means that the nodes collectively need a timeout. And so that issues the timeout certificate instead of the quorum certificate that enables it to move to the next rank, but not the next frame. And then it'll finally move on to the next frame because it picks a different prover and moves on from there. And that's what we're basically seeing in prod right now, is one of these archive nodes being down. So as this continues, we will start to see more of these pending frames appear. Okay, deciding to propose. Not the leader. Generating the proposal as a leader. Okay, so now we can wait. On my coil, it's just one of those disposables. I'm not a big fan of them, but it's what I have on hand at the moment. I don't live in the boonies, but I do live in a place where it's actually kind of hard to get a hold of decent e-cig stuff, so yeah, I'm stuck with what I got. Okay, that triggered a timeout, and so now we're moving on to the next rank. I'll have to investigate what's going on with that, but TLDR, once it does get to the next frame, eventually this node will snap ahead to the latest because it's no longer operating in archive mode. Now, the consequence of that is that it requires a string of 360 frames contiguous in order to actually surface, oh, hey, this is the full realized state of the global side of the network. Now I can process all of that and move ahead. And you can see, yeah, now we have caught frame 13. So it's just going to keep doing that, and then we're going to see something else happen afterwards. I'm not going to sit here for an hour and wait for this to happen. I'd rather just show you what will happen because that would be a better use of everybody's time. So I'm going to go ahead and hop over to Visual Studio Code. And yes, somebody memed about the fact that I was using light mode and that's why things took so long. I actually don't use light mode normally. I use light mode when I'm doing these presentations because otherwise the stream looks kind of washed out and it's hard to see for folks. All right, so let's go ahead and look at the event distributor loop. So what's happening is on the time reel, and you can see what I was talking about in here, where we're processing a pending frame. You'll eventually see it trigger a state when the time reel has gotten enough frames and it's saying, oh, I've snapped ahead. It will generate this event called control event global new head. And when it gets that, it'll react to it by doing a couple things. First thing it'll do is it will look at all of the shards that exist locally. Now, these shards are based on the genesis state. So initially, the shard coverage is going to be just the, on testnet, is just the one single shard of the Quill token. On mainnet, it's already divvied out into 4,096 shards because that was a reasonable estimate for a sufficient number of nodes that were going to be joining the network based on our previous statistics. And so from there, it checks the shard coverage, sees what it could potentially, propose that its workers can work on. In this case, being only one shard, it's only got one choice to make for all of the workers that it has. And it will proceed to, one, get its identity key. If it doesn't have it, which means it generates an error and it hasn't sent a key bundle before, it will go ahead and publish the key registry. 2106 will do this more often on a regular basis. But this is just, the behavior of 2105. And so as long as it's done that, great, then it moves on, and then it ranges over its workers to proceed to evaluate on each worker whether or not there's anything that it can propose to join. If it's already joined or already proposed to join, then it will do nothing. But if it hasn't, then it will proceed to try to join shard. And so when it does that, by the way, if any of these things fail, you'll see a failed to check shard coverage error. You will see an error when it's publishing the key registry. You will see it fail to retrieve its workers. But all that good, it goes to evaluate for proposals. And from there, it will proceed to get a little bit of info about itself. One, check out its effective seniority so that it knows how it's going to rank against others who have already proposed to join that same shard. And from there, it'll calculate a score and then proceed to decide whether or not it will go ahead and join. And when it does so, it will then try to sync all of the data that corresponds to that shard, so it will be ready. It will proceed to generate its, oh wait, this is the confirmation side, my bad. Here we go. Oh, where are you? Work around from this side. Oh, yes, because it goes all the way to the bottom and there's no proposal. Okay, cool. Yeah, this function could use a little bit of refactoring. So anyway, it queries the proposer, which is essentially taking network information, like what is the current world state size, so that it knows how much Quill is being issued every interval, and then what its own information is about its workers, like seniority and so on, and then proceeds to take all of that information and plans and allocates. And when it does that, it will get a response back such that it can proceed to decide to join. And when it decides to join, you'll see a message decided on joins. It's not very creative. Or you'll see could not decide shard allocations if there was an error. And when it does that, it's emitting a global join message. And you can see the global join, like the global prover join logic here. It's very simple. It's literally just querying the hypergraph to say, hey, am I already here? Can I put anything here? Can I choose to join this? And if there's any additional merge information, like if you had a bunch of keys from the early days that you want to merge together into a single block of seniority, you can do that, and it's got logic to handle that. And then it will proceed to actually generate the proof join request as a proof. And then from there, the validators on the global side will receive the message, verify it's all good. If it is, it gets included into the next global frame, and then Materialize actually runs and performs the set operations on the hypergraph corresponding to the global intrinsic address, which is just 32 bytes, all Fs. And that's it. That's the join process. So a lot of people have asked, since they've already upgraded and they're watching like the performance of their nodes, the one thing they're seeing as a standout is, hey, my my CPU is doing nothing. And it's because, yes, the initial enrollment's a 24-hour period, or more accurately, more like a 36-hour period right now. And during that process, it will decide to join, and then sit there and wait. And it will sit there and wait until the, in terms of network time, the 24th hour frame has passed. And from there, that's what enables it to then proceed to confirm. And that's what I was actually looking at earlier by mistake, which is part of the evaluate for proposals, and it will proceed to do that. And in the confirmation process, it will make one of two choices. It will choose to either confirm, which means that it re-examined the state from all of the different allocations that were attempted based on seniority. So if you joined early, you had low seniority, and then another set of provers joined on your same shard, they have higher seniority, they would end up at ring 0 while you would end up at potentially ring 1. It'd be worth less in terms of overall quill gain, and so by consequence, your node could potentially benefit better by reproposing for a different shard. And so that logic will do so, and it will either produce a confirm if it's good, or it will produce a reject if it's bad. And in that process of producing the reject, it'll actually bundle all these calls together. So if it needs to reject, it will produce a reject and a join message at the same time. So it's not wasting any time trying to find the most valuable shard to join. And if you want to see the logic behind that, because it's not particularly complicated, you can find it in the, I'm trying to remember where I put it, because I think it's here, yeah. You can find it in Consensus Provers Proposer, actually Node Consensus Provers Proposer from the root level of the repo. And you'll see the basic logic. It uses an injected world sizer, and what that literally is actually just an injected hypergraph instance, so it can query for what the total world size is. But the basic premise is that it will, given the information about your workers, it will proceed to generate a series of planned joins that it should do. And the logic is, it's entirely contingent on your configuration. The default configuration you've heard me talk about in the past is reward greedy. So in other words, it will optimize for the most rewards that it could possibly earn. And then the other alternative is data greedy, which is what archive nodes will do by default too. And the purpose of that is to try to maximize the amount of data that it is collecting and covering for the network. And there's different intentions behind each strategy. At the beginning, they're gonna be basically the same for rewards. But as time goes on, the optimization is going to be towards rewards for most nodes, and by consequence, that will start to produce a meaningful difference in what the overall allocations of shards end up looking like. And so that's basically it. Like at the moment when the network's in this state, that's basically all you're gonna see. Afterwards, you'll start to see things fan out. Yeah, you can already see that it's getting more frames. You can start to see things fan out, and from there it will proceed to, once it has successfully confirmed the join, it will then respawn these workers, which you're just seeing messages about because my disk is almost entirely full. You'll see them start to spring to life, and you'll see their CPU rate go very high as it proceeds to start working on that given shard of the network. And so I'm going to stop these because I just realized that I'm maxing out my CPU while I'm trying to stream to 2 different platforms. So if this was a little bit choppy, I'm sorry. That's why. It should be better now. But the idea is that once it does that, it then spawns the workers. You'll see this data IPC service. In that, you'll have a command that will perform a respawn server. One thing that's important to know is if you looked at the upgrade guide, you'd see that different workers are all exposed, unless you did the proxy, but it's still technically exposed through your master proxy. And so these are all RPC calls. So the respawn server is an RPC call. And so if you're wondering like, hey, couldn't that mean that somebody is able to just send a command to my data worker and have it respawn my node to whatever filter I choose? No. The only way that you can actually do that is that the master node that is talking to your worker nodes has the same peer key. And without that peer key, it won't authenticate. And so there's this concept called the peer authenticator. I think I talked about it in a previous stream, but it literally can be delegated down into all the different RPCs that exist, such that you can choose, like in the case of this service itself, only yourself can actually be authenticated with it. Nobody else can call it. And this is cryptographically bound. Like, you can't forge a request through any other means. Like, you have to, if you were to successfully authenticate with it, you would have to actually have compromised that peer prover key. So that brings us to, in the respawn process, it will proceed to literally shut down the entire app shard worker and then restart it with a new filter. And the filter is literally the shard address. And so when it does that, you'll see, just like how all of these were actively, like, once I scroll back up, we're active, oh, sorry, this is worker 6. We're actively building consensus around the frames of global state. You will see the app shard workers will be doing this exact same thing, but the information will correspond to a filter that is the app shard. And so it'll look exactly like this. That's why I'm showing it in the first place, because otherwise people would be like, why the hell does it even matter that you're showing me what a node that I'm not even running is doing? That's why. Because it will look exactly like this. It will have the same concept of rank. It'll have the same concept of quorum certificates and timeouts, and it will behave in the exact same way for how the next leader is selected. The only difference, and this is my big middle finger to the people who were super extractive during 2.0, and this is one of the big lessons learned that I wanted to talk about, is there is no way to act like a regular worker and forge that worker's behavior. So one of the problems that we ran into in 2.0 that really pissed a lot of people off is that as a proof of work based protocol, naturally there are a group of people who will proceed to try to, like, basically game this out. Like, how can I optimize this code to get me the maximum amount of whatever the work unit is so that I can get as much rewards as possible? And one thing that came to a head is that the way that the proofs worked in 2.0 were probabilistic proofs. And what that meant was that, you know, it chooses, because you'll have potentially thousands of workers. Some people had hundreds of thousands in a giant cluster. And what they would do is they'd recognize that it chooses a random set of workers such that it was able to get the proofs that it's producing at a small enough size that we didn't have to, like, do the VDF verification calculations for every single worker. Not to mention how large it would be to have proofs for every single worker. Each proof is 516 bytes. So for a, I'm going to have to do the math here because I'm omega dumb, but that comes out to roughly, or not even roughly, precisely 49 megabytes for 100,000 worker cluster. Every single frame. That would be absurdly expensive on traffic. And so what we did was a probabilistic proof. Instead, it would take a challenge that was produced entirely based on the next iteration of this proof system. And it would work through the tree backwards and find log n, where n is the number of workers, number of different tree entries, and it would produce a Merkle proof based on the commitment that was previously broadcast in that proof iteration, such that it could choose essentially like a limited number of proofs that is a sufficient bar to convince a verifier that they are actually running that many workers. And so by consequence, that meant that there was a probability that you could produce a proof that if, for example, you had a worker fail, like 1 of 100,000, and that worker failed for that iteration, you could just shove 0 bytes in there or random bytes in there. And by consequence, when it created the commitment in the Merkle tree, you would end up getting a scenario where 99,999 worker commitments were valid, 1 was not, but by pure, percent chance, it's not likely to be picked. And so it was safe to do that. And so there were people who came up with an optimization game, playing on the percentages, such that they were able to produce very frequent proofs, even under the condition that they had workers that were frequently failing. And technically, that was the rules of the game. And so by consequence, that led to a bit of a schism. People were very upset about that, and we were actively trying to solve that, which is actually what led to us having the logarithmic proofs that were much more likely to induce failures. And when those failures were detected, that would result in a complete boot of that user from the entire proving system. And so it's very weighted against trying to misbehave. But we took this one step further, because one of the things that I'm not necessarily the best at code, but one thing that I do well is math. And so when I have to deal with people who are being a bunch of fucking dickheads, I'm going to proceed to find math to outsmart them. And so by consequence, we amended the process for how app shards produce their output frames. And so in the process of running a worker, you will see, oh, where did I put it? Let's go ahead and go to the global side so I can show that first. So on the global side, you will see this. So when you prove the next state as the leader for that given iteration, you'll see that it does this prove global frame header where it literally just produces a Veselovsky VDF proof. And that's it. And that's what generates the new header with the new output, and that sufficiently convinces a verifier that that particular node has spent that particular amount of time. But on the app shard side, one thing that is crucial here is you could potentially have, like up to 36 provers in a given shard. And that means, like, if you balance it, 1 out of 36 provers, well, that means 35 provers aren't actively having to contribute for that round of consensus. And so we amended how the signatures work. And so the way that it works as a voter on the global side, you will see that there is a sign vote. And when it signs the vote, all it does is it creates a BLS signature, makes the vote message as the signature data input, produces the signature with sign with domain, and then emits creates the proposal vote, which then gets broadcast. Cool. And on the app side, we take it one step further. So we'll have the proposal vote, but you also will have to inject this proof. Now, if we waited right at the end for this proof to be generated at the sign vote phase, then every single phase of consensus on the app side would time out. It just would be untenable. So instead what we do is we proceed to have a proof cache, and those proofs are generated at the same time that every other, at the same time as the dedicated leader has been chosen. And we know this because we are calling the same leader for ranked function that every other participant is. So if we know that we're not the next leader, then we can go ahead and proceed to get our prover address, confirm that this is correct, get our index for the position, in the overall set of workers. So 1 of 36, like potentially 24 of 36, whichever one you are, you'll proceed to get your index so that you know that you're ready to go, and you can calculate what is called a multi-proof. And this isn't the same kind of multi-proof as the KZG multi-proofs that I've talked about in excruciating detail before. This is a VDF multi-proof. And the trick is leveraging the quadratic imaginary integer algebra that we're using to do the VDF proofs in the first place. So this enables you to generate a contribution of a VDF proof using the same amount of compute that the next leader is also having to do, such that when you produce that output proof, you are concatenating it with your signature payload in the vote, so that when the votes are tallied and put into the quorum certificate, the output quorum certificate also has a combinatorial proof, like VDF proof, that can then be verified to confirm that every single participant is actively participating and not faking it. So to that I say, suck it. All right, so this is essentially the series of lessons learned that were important for leading Q2.1 into being Q2.1. So the next thing that we should talk about is what's next. So like I already mentioned, there is 2.106. 2.106 is going to be an update that is important. And you can actually already understand why that update was important for one simple thing. If you have been running a node for 2.105 and you accidentally restarted it and saw that the database did not successfully load an entry, then you already hit the bug. So 2.106 resolves that problem, because you'll notice as I restarted this node multiple times, didn't have a problem with it, and I didn't have to clear the store to do it. And that's exactly why, is because That bug has been fixed. The other thing we're going to be fixing is around the master proxy thing I was talking about earlier. There's a weird state that they can get in. Thank you, Jack, for letting me know about what you were experiencing on your node. That was super helpful. But that's basically it for the patch release that we're going to have out shortly. That's cool and all, but what comes next? And so if you've been following the project for a while, you know that 2.1.1 is planned for the purpose of taking some of the items that we shelved for the 2.1 update and bringing them back in. So the encrypted query evaluator, instead of this weird pairwise walk through the hypergraph, it's now a oblivious RAM or ORAM based lookup that provides greater privacy. Obviously, because these queries are being done through the onion routing, we already have a decent amount of K anonymity, but that's helpful but not good enough. I'd like to introduce full analytic privacy through the use of that ORAM query support. We might throw in a few other goodies, but that's the important thing for 2.1.1. 2.2 is where we get into some of the bigger objectives, like supporting certain types of streaming data that's encrypted. 2.3 is where we start to introduce, I'm trying to remember the game plan, because I believe 2.2 was going to have the iterative execution for continuations so that we could do things like MetaVM, but that might actually be 2.3. Somewhere in between those two, that's where MetaVM falls along. And the reason why I'm a little bit ambiguous about it anyway is because one of the really cool features of Q is that you can actually run a shard that is not consensus bearing. It will impart state at the global level, it will impart a commitment, but it doesn't actually participate in normal consensus, which enables you to have data that is addressable by the network and provable by participants on the network without actually having to maintain the burden and cost of paying for that shard to exist. So you'd basically be eating that cost yourself, but it gives you the ability to do a lot of really cool tricks. And so what's coming up this week is actually an example of this. The first being, obviously we're going to have Q storage, we're going to have QKMS, and those are going to leverage alt fee basis app shards for certain tiers of users. That way we don't potentially pollute state with a bunch of crap that somebody's not necessarily going to pay for because they have the free 5 gig account. But there's also going to be our bridge. And so later this week when the bridge is stood up, we're going to need a bunch of state in order to support bidirectionality from Ethereum. And so the purpose of the alt fee basis app shards is that we can actually run a execution node for Ethereum, have it generate the output execution state into the KZG polynomial commitment format that we use on Q, and then suddenly all that information just immediately being pulled in as an alt fee basis app shard, costing literally 74 bytes of data that gets rolled into consensus as part of the overall 19 kilobytes of global proof state. With that information alone, you can now prove anything about the state of Ethereum's network, which lets you do a really cool thing for bidirectional bridging. It means that whatever the consensus window is for finality, in Ethereum's case, there's different, it's probabilistic finality. So there is technically the epochs for the consensus layer itself. And so generally the way people look at it is that after 2 epochs, it's truly finalized. But a lot of people will take it from a probabilistic perspective and instead say after 6 or 7 blocks, it's probably good for low quantity transfers, anything that's not high value. But for anything higher, you might need to wait a little bit longer than that, but still not the 2 full epochs. In the case of a lot of exchanges, though, they'll wait the full time. And for Q's case, same thing. But the purpose is, once we have that full guaranteed finalization, that state gets imported into Q, and we can now refer to it. And by referring to it, we can actually make it possible to support bidirectional bridging, not just of the Quill and wrapped Quill token, but any other ERC20 for the most part. There's a few exceptions, like those weird rebasing tokens where state changes in really weird ways. That one we can't do. But if it's a standard ERC20, we can do it. And similarly for an ERC721. So if you want to take a collectible, or a collection of collectibles, they use the term NFT, I hate that word. But if you want to take a collectible and bring it into Q, and you want to actually take it one step further, because most of these NFT projects do not actually store their visual data on Ethereum because it's too expensive. Instead, they store it as like an IPFS hash. What you can do is you can actually take the IPFS data, the ERC721, and you can go bridge it over using the trustless bridge into a collectible that lives on Q, including the data. And the really cool part about it is all of that can stay private. So when that data is bridged over, it is bridged over in an encrypted format. So the rest of the network doesn't know what you've bridged. You submitted a KZG polynomial commitment, like proof to that commitment, my bad. And so by consequence, the network knows whatever the hell you just did was real and correct, but they don't know what you actually did. And so that's a really powerful concept. It basically gives you the ability to take any collectible, any token from a EVM compatible network, at least with this process, and turn it into a private token immediately, or turn it into a private collection immediately. And that's a really powerful concept because there really isn't another network that's done that before. And so in terms of like, a glimpse at what's next, it's these kinds of things that are going to like blossom into very unexpected and serendipitous applications. Things that like, sure, I just like described something very simple, but I'm sure that somebody just heard what I said and they are going to run with that and be like, holy shit, I can build all these cool things. And I can't wait to see that and I can't wait to support you. But in the meantime, like that's what's coming next. So just wait for what comes after. And one of the things I wanted to mention is that process to support EVM chains doesn't just apply to EVM chains. You can apply it to Solana. So like our longer term goal is to expand the bridge not just to ERC20s and ERC721s, but also SPLs. And that extends to other kinds of chains as well. So not even actual like regular blockchains, but chains that are for other purposes, like social media chains, such as Farcaster. And that brings us to talk about Quorum Mobile. Why do you ask? Because Quorum Mobile, this is the one feature that I was leaving behind for the final preview before the beta goes out this week. Quorum Mobile, as you can see, I just loaded a bunch of posts, is a Farcaster client as well. And so what this lets you do is it gives you basically a kind of portal that for all of your conversations and messages, they stay private. But for your public posts that you want to, shout out to the world, you'll be able to actually say this and post it, and then share it and remix it and bridge it into Quorum Mobile itself, or the Quorum protocol itself. So go ahead and do that. You can see it says, hello from Quorum Mobile. Let's go ahead and take a look and see if I goofed during a live demo or if it successfully posted. Look at my profile real quick, and there we go. So that's the last big thing, and the reason why I even bring it up is because I was talking about mini app support before as a really cool thing. Like you have mini apps that already exist and have lots of cool different token integrations, and we're going to be able to empower them with all these extra privacy features of Quilibrium itself. But one of the things about discovery and surfacing those comes from its original ecosystem, and that would be Farcaster itself. You can see that I've gotten some likes. And so this is going to be crucial for completely creating a comprehensive flywheel. You can create applications on Q. You can expose them as privacy preserving, encrypted mini apps, kind of like Tor hidden services. You can present a portal to the world as a mini app in a post on Farcaster, and that can bring users that are on just Farcaster over to Quorum or over to your app on Q. And so this is what I was getting at about how all of this starts to accumulate into something so much larger than the individual pieces itself. And I'm not going to use the S word for that because I am so tired of people who use that. It's just a stupid ass buzzword. So instead, this is essentially the surprise thing that I wanted to bring up. let me take a look real quick if there's anything else that I wanted to mention. Otherwise, I think that actually brings us to a conclusion after only 1 hour. I thought I was going to be sitting here going just through the dev deep dive for an hour and a half itself. Guess I was a little bit fast. I'm going to go ahead and also take a look at the questions that have popped up. I've got a couple of different places that I'm looking. Oh, where are we on the countdown? I'll actually start to post a regular update of that. I can't check it right this second because I'm not connected to any of the nodes that are touching mainnet. It's just general security practices. Don't use your streaming device to do things that are high security. But I will. I'll send that afterwards. Let's see. Oh, cool. We just hit 6,666 followers on Twitter. That's fun. Okay. Anything else? I swear, I need to improve my streaming setup because this is just a pain in the ass. Okay. Oh, hey, Husky. It's been a few minutes. I guess your theory didn't work out, did it? Okay. I think that's all the different channels that I was streaming on. Might be adding more soon. Let's see. I think that's it. Cool. All right, cool. Well, I guess that brings us to the end of the combined dev talk and enrollment recap. Just as a heads up, like I said at the beginning, like I said in the middle of it, things are running a little bit slow because we do have one archive node that is currently down. I'm actually going to be working with that archive node operator to get that up and running, and so it'll resync and catch up with the rest of the herd. And when it does, then we'll see frame times reduce. But it does mean it's very likely in the meantime that we're going to be ending up with about a 36-hour enrollment, like initial enrollment window, rather than the 24 raw hour. Oh, okay, cool. As far as privacy is concerned, can you give a layman's answer as to how private transactions will be? So, for instance, suppose there is a DEX on Quill native. Would a site like DEX Screener be able to see buys and sells if all transactions are private? So this is where it gets a little complicated. The short answer is yes. It is going to be, or not yes to that they'd be able to see it, but the short answer is yes to it's going to be private. The right answer is it depends. And the reason it depends comes down to application design. Because this is a generalized compute engine, it is possible for somebody to make a application like a DEX that is not properly designed to be private. We make it hard to do that, but it is possible. So even in the world of Q, like, you still have to be careful and audit what you're interacting with, because there's still going to be, there's still the possibility somebody could code something with a bug. There's still the possibility somebody could make something intentionally insecure. It is going to be kind of a requirement, especially early on, until we have a very large community in the same way that other ecosystems do, where there are people actively watching out for these kinds of things, that, it has to be built correctly, and we've got to be careful, and it's on us all to make sure that that is done, especially me. And so, in theory, if you were to build a simple DEX, let's say that you just use QCL to create these atomic swap arrangements between two different parties, or you create a much more complicated arrangement with a tripartite kind of interaction that enables an order book flow to exist. If you do this right, and you are storing this data in a way that is sent to the hypergraph in its encrypted form, not using a publicly known read key, but rather a key that is potentially the arrangement of multiple parties, or some sort of interaction layer that does the order book matching, or whatever. It's, again, design dependent. Then yes. all of those transactions would be private, and a screener like Dex Screener wouldn't know anything beyond, hey, this application that does trading had transactions. Not what they are, not how many, not who. Literally nothing is visible to them. And the reason is because of the way that we built our token primitive. And that's actually kind of one of the crux of the issues around building secure applications. One of the things that I thought about, and it was a big problem that happened early on in token applications on like Ethereum, and definitely took a while for the Solana community to figure stuff out. One of the problems in creating a token is that it is possible to do many things with many foot guns that will screw up your launch, cause somebody to potentially to be able to like infinite mint. All these things exist because bugs exist, and because the application is generic enough that you can put anything, as long as it conforms to the interface of an ERC20, as an ERC20. And so what we did instead is we actually simplified it. We made the token itself, like the application for a token, we made that hard-coded in the sense that it is a very specific pattern. You have to very specifically configure it, and it gives you lots of knobs and levers, but those knobs and levers will never let you make a mistake that allows the wrong thing to happen. Short of if you have like a, mint with authority and you publish the key, well, there's nothing we can do about that. That's a real foot gun on your part. But anything beyond that is how we ensure that at a minimum, that if you put a token on Q, using the token application and not like doing something crazy with QCL, as long as you build it with the token intrinsic, the actual transactions are private. The quantity, the destination, the refund recipient, if it's a acceptable token, like one that allows pending flows, all of that is private data. And so that's the kind of way that we think about it is, for all the things that we can make it easy for people to do the right thing to keep people private, we'll do. But for anything that goes to the extent of building complex applications where a lot more logic comes into play that involves lots of external user input, there's ways you can get it wrong. But again, with all these things, we're going to be doing our best to give a best faith effort to make things work. Okay. Are web apps possible to be hosted or just static HTML files for now? For instance, having a web server running, would it be possible on Q? So I'll actually get to that in our more advanced streams after we're done with all this enrollment stuff. There is kind of a way to do it under the, if you're using, for example, Q storage, no, those are static files. But if you're building something that uses Q storage as a loader for a single page application, and it uses the other Q SDKs and JavaScript to interact with the protocol itself, then yeah, you can actually come up with a whole bunch of different interactions that will let you run dynamic web applications through Q using the SDK to perform those interactions. And that's something that you couldn't really do with, say, Ethereum, because it's just too expensive to put that much state in the network. So yes, it is possible, and we are going to actually cover that as a fun demonstration. But it's not quite as simple as, like, if you go to AWS right now and you deploy a Lambda, we don't have Lambda yet. We're going to have something like it called f of x, and it will let you do those things. But that's going to be ahead of now. Right now, our focus is to roll out Q storage, QKMS, Quorum Mobile, and so on. And then we'll be able to add those things in. And those things, like f of x, are going to be doing those same tricks that we're going to show in those dev streams. So it's going to be the same concept, just a little bit more polished for people who are accustomed to building apps in like JavaScript or whatever. Cool. I think it covers everything that popped up. Let me double check. All right. Okay, folks, well, I guess this wraps it up. So I'm going to go ahead and close it out now, and you're going to see Streamlabs pop up because I am living in a cursed world where I use applications that are absolutely cursed. So yeah, thank you all for watching, and this time we will be back next Sunday night for the US, Monday morning for Europe and Asia. But I'll see you then, and we'll be covering, the aftermath of enrollment and some very fun deployment on Q. I think the first thing we're going to do is we're going to launch a meme coin. Let's find out. All right, I will see you all next time.